So let's talk about how to frame this as a Spark problem and actually distribute breadth first search across our entire cluster potentially. So the first thing we need to do is to represent our data coming in as these nodes that we talked about in the previous lecture. So for example, an input line might be of this format. The first number is some hero ID followed by a list of the other heroes that hero has appeared with in other comic books. So we want to structure that in a way that represents one of these nodes in breadth first search. So for example, we could structure this as the following tuple of tuples, if you will, where the first element is the hero ID that we're talking about, the one that's basically represented by this node, followed by a list of all the other hero IDs that are connected to this hero. So there, imagine a virtual line between 5983 and 1165 and 3836, etc., etc. So these are all the connections that are connected to our hero. And that itself is within its own tuple to keep that all self-contained. The next element in our tuple will represent the distance associated with this node from the character that we're measuring distance from. And initially, we set that to infinity. There's no way to really represent infinity here, so we'll just set it to a really large number. In this case, 9999 will be our stand-in for infinity as the initial distance value. And we need to associate a color. Remember, our nodes could be white, gray, or black, where white represents an unexplored node, gray represents a node that needs to be explored, and black is a node that's already been explored. So initially, every node is white. So that's an example of how we can represent these lines in a format that is consistent with our concept of nodes in a breadth first search. So now actually going through that breadth first search algorithm can be thought of as a map and reduce operation. The mapping function will take care of converting those lines into the BFS node format that we just talked about. And that code might look like this. So we just need to split it up by spaces, convert the hero IDs to integers and the connections to integers, build up an array of connections that are all the connections associated with that person, set the initial color to white, set the initial distance to 9999, and if the hero ID is one we're starting with, the initial case for the one we're starting from is to color that one gray with a distance of 0, but everything else should be white with a distance of infinity as our initial case. And we just return our tuple structure that we talked about with the hero ID, and then furthermore the array of connections and the distance and the color. Now it's maybe a good idea to talk about the history of distributed computing here a little bit. So note that we're using a MapReduce paradigm to sort of think about this problem. Where does that idea come from? So way back when Google was first dealing with large-scale data analytics and the need to process data that could not fit on a single machine, they invented MapReduce. And MapReduce was pretty much limited to map functions and reduce functions. That's what it did, right? And we've seen examples of mappers and reducers in previous examples in this course, but it used to be that's pretty much the only trick that we had up our sleeves. Hadoop was built on top of the concepts that Google came up with, and Hadoop, it also has something called MapReduce. It's actually called MapReduce, one word. That's an essential component of Hadoop itself. The problem is that MapReduce wasn't very smart about its optimization, and that's where Spark came in. So Spark initially was just sort of a faster alternative to MapReduce. So that's where the initial RDD interface of Spark came from. You'll notice that RDDs have a map function and a reduce function available to them, and that's why, because they were trying to replicate the functionality of Hadoop's MapReduce functionality. Now later on, over time, when we got to Spark version 2, that's when datasets and data frames were introduced. Data frames came first, actually. And that's when we started to say, hey, let's think about these in terms of SQL operations. SQL was kind of becoming the common language between data analytics software packages at that time. So even for things that were distributed and technically weren't suited to relational database operations, SQL was still becoming the common syntax between all these different platforms. So we saw this evolution from MapReduce to Spark that was sort of built as an extension to make MapReduce better, to Spark becoming more of a SQL-style interface. But not everything is a SQL problem, right? So we still have that more lower level functionality of MapReduce available to us that we can use to solve more general purpose problems such as this one. I can't write a SQL command that says compute the distance in a graph between any two nodes, but I can frame that as a MapReduce problem, so that's what we're going to do here. Again, it's about choosing the right tool for the job. Even though we can do this with a data set, and I'll show you that, in this case, using RDDs and their lower level mapping and reducing functionality is going to be the more straightforward approach. Okay, off of my platform. Let's talk about the implementation some more. So just like we walked through in the slides for breadth first search, we're going to go through things iteratively. And for every step, every distance, we're going to look for all the gray nodes and expand those gray nodes out, color the nodes we're done with as black, and just keep incrementing the distances as we go. So you're going to see a big old loop that just iteratively goes through that graph over and over and over again, looking for gray nodes and processing those gray nodes accordingly based on the rules that we defined in the BFS algorithm. All right, so again, we're just framing this as a map and a reduce job. So every time we increment through our algorithm, the mapper will increment the distance by 1, and it's going to look for gray nodes. If it finds a gray node, it's going to look at all the connections of that gray node, color them gray for future exploration, and initially they will have no connections because they need to be explored to build up those connections on the next iteration. The gray node it just processed will then be colored black, and it will copy the node itself back into the results to make sure that we don't lose it. The reducer's job will be to deal with all those cases where we have multiple paths going into the same node, many connections. So we need to combine together all the nodes that exist for the same hero ID. And if there is a case where there's multiple connections, we want to preserve the connection with the shortest distance and the darkest color. And as it's reducing things, it will preserve that list of connections from the original node to make sure we don't lose those on the next iteration. So that's how it all works from an algorithmic standpoint. But how do we know when we're done? So here's where we are going to introduce a new concept called the accumulator in Spark. So an accumulator is basically a shared counter across all the executors in your cluster. So if you need to have sort of a commonly held counter, if you will, or a flag of some sort, an accumulator can do that. It allows many executors to increment some shared variable across the entire cluster. So here's an example of the syntax. I could say hit counter is a long accumulator named hit counter, and by default its initial value will be 0. So as we're going through our algorithm, our iterations are going to be distributed throughout our entire platform, and any individual executor might hit upon the character that we're interested in. So when that happens, that executor needs to somehow signal back to the driver script as a whole, hey, we're done, we actually got a hit here. So we can increment the hit counter accumulator in that case to indicate that it actually found the character that we're trying to find the distance from to our original character. So when we're done with each iteration, we just check if the hit counter is greater than 1, and if it is, we know that we're done. And sometimes we'll get a hit from multiple directions, and that hit counter might be more than 1, but that's how we know that we're done. Those executors can signal back to the script, hey, I got a hit, and it can keep track of how many hits by having this shared accumulator across all the executors. So that's a lot to wrap your head around. Let's go off to the code and see what it looks like.